Hi everyone, I'm Layla from Princeton Satellite Systems, and today I will be explaining our manned Mars mission architecture using Starfire. This is a compact fusion reactor for both power and propulsion. This presentation was given at the AIAA ASCEND conference last May. So I'm going to walk through why it matters for a mission like the Mars mission, and then I'm going to dive into the theory and architecture behind our fusion reactor Starfire and compare it to other power systems. And finally, I will demonstrate how this can enable a reusable human Mars mission that significantly reduces transit time. Sending humans to Mars is the next giant leap in human achievement and space exploration. However, to actually get there, there are a lot of challenges that remain unsolved. And they're not just engineering challenges, there are also a lot of health risks that are imposed on the astronauts. This is mainly because of the deep space travel, which exposes them to radiation and microgravity. This causes severe health risks like bone loss, organ damage, cardiovascular deterioration, and damaged DNA. This is why we need to minimize transit time as much as possible. And it's also why we can't rely on methods like chemical propulsion, which would take around 9 months for us to get to Mars. Our fusion reactor concept can get us to Mars in 67 days, which is a significant reduction in transit time. And this can ensure that the astronauts arrive to Mars in healthy conditions. And because our reactor is dual mode, so it's both a propulsion and power system, we can use it for surface power on Mars, and it would provide 1 to 10 megawatts of surface power. This could enable us to have a sustained established presence on the Martian base, and it would also allow for other scientific operations on Mars, as well as fuel production during our ascent stage, which I will explain in more detail as I get to the mission architecture. Before I get to the mission architecture, I want to briefly go through how our fusion reactor works. So these two diagrams summarize how it could work both as a propulsion and power system. So in the propulsion system, you have a magnetic nozzle attached, and in this case, we use the heat from the fusion core to heat the hydrogen propellant that is injected. And this is expanded and accelerated through the magnetic nozzle, and you can modify the thrust and the exhaust velocity based on your specific mission needs. As a power plant, you close the exhaust end, and Starfire drives a closed-loop Brayton cycle. The heat to drive the Brayton cycle is extracted from both the fusion core and the vessel walls. Our working fluid in this case is helium xenon. So how our fusion reactor works is very different than the most known fusion concepts like tokamaks and stellarators, and these are these building-sized reactors. In our case, ours is significantly smaller, so it's less than 2 meters in diameter, and it is based on the field reverse configuration architecture. And this architecture depends on a background mirror field with field reversal that closes field lines to confine fusion plasma, and this is where fusion reactions take place. There are many ways of achieving the field reverse configuration. In our case, we use what is called an odd parity rotating magnetic field, and this is based on the Princeton field reverse configuration invented by Dr. Sam Cohen. So the architecture consists of a linear array of superconducting coils encased with cryostats and two superconducting mirror magnets. And you have the stainless steel vacuum vessel that encapsulates the fusion plasma. And then you have the odd parity RF antennas that generate the odd parity rotating magnetic fields, which I will explain in a second. So if we take a cross section at one of these antennas, you have the rotating magnetic fields, which produce azimuthal electric field, which induces a current loop that produces magnetic fields in the opposite direction to the background mirror field. An odd parity in this case means that if you take the midplane, on the right-hand side, it would rotate in one direction, and on the left-hand side, it would rotate in the opposite direction. And the reason we do this is because if you take into consideration the background mirror field and the current loop we generate, that induces magnetic fields in the opposite direction, which causes the field reversal. You can see here that on the right-hand side, the field reversal is facing one direction, and on the left-hand side, it's facing the opposite direction. So these Odd parity rotating magnetic fields really ensure the closure of these field lines, which improves the confinement and heating of the plasma. So in this stage, you have the core, which is where fusion reactions take place. And then you have the scrape-off layer, which is the area around it. And this is where lower temperature plasma mixes with ash and is extracted. Now, the reason why this configuration is very beneficial for our mission is because the first thing is that the natural uh, axial flow of plasma in this architecture is a natural fit for jet propulsion. It is also a very simple and small machine because it is linear and it's also less than 2 meters in diameter, and it's low hazard. It's low hazard because it is high beta in nature. FRCs are high beta. Tokamaks, for example, are low beta. And low beta means that the plasma pressure over the magnetic field pressure is low. This restricts the tokamaks from using advanced fuels. So tokamaks usually use DT fuel, and this causes damaging neutrons because DT has high energy neutrons in its reactions. In our case, because we're high beta, we can use advanced fuels like deuterium helium-3, which is the fuel we use. So this has no high energy neutrons. However, side DD reactions can produce tritium, and that tritium can fuse with deuterium, which can cause DT reactions, which produce high energy neutrons. But because our reactor is small in size, we can actually extract the tritium because it has a large gyro radius. So we can extract the tritium before it fuses. So we really do minimize the neutron production in our reactor, and this makes it much safer, and it also requires significantly less shielding for a more compact device. We also have maximized specific power. So we're talking in the range of 10 times more than solar electric and 50 times more than fission electric. And this is mainly due to because it is a direct thrust uh, propulsion system, so there are no heavy power electronics required or conversion systems. So this table summarizes the comparisons between the different power systems with our fusion reactor. So as you can see, it has the highest specific power. We're talking in the range of kilowatt per kilogram. Princeton Satellite Systems has had over 10 years of sustained research in fusion. So we've had many grants with the Department of Energy, DARPA, and NASA. These are some examples. And we also have a running experiment at Princeton Plasma Physics Lab, which is conducted by Dr. Sam Cohen, as well as high fidelity simulations. As you can see here, we've done particle and cell simulations for our fusion reactor. Starfire has overall secured $4.5 million in non-dilutive government funding, and this year we won a 400,000 DARPA grant for the fast modeling of fusion plasmas. So now we want to see how this reactor can be used in a notional Mars mission architecture. And one of the main benefits is that it is highly reusable, and this is because of the low neutron production, which extends its lifetime. And also, its dual mode allows it to be used as a propulsion system and surface power as well, which allows us to do things like fuel production for our ascent stage. And this is done using the electrolysis of water on the Martian surface. I will also talk about that in a second. So the concept of operations involves three NASA SLS class launches. So this diagram shows the fitting of our components in SLS fairing. So the vehicles will be assembled in low Earth orbit, and then we will have a slow cargo transport that is launched years before the crew transport, and then we have a very fast crew transport. The main vehicles in each mission will have a Starfire powered transport, a Viking-inspired lander, and a crew ascent vehicle. So the difference between the cargo and the crew transport is that cargo really prioritizes efficiency. So it is in a low thrust, high exhaust velocity mode. It would reach Mars in around 1 year. And this is again before the crew departs with around 2 years. And then for the crew transport, to minimize the health risks on the astronauts, the priority here is speed. So it's in a high thrust mode and it has no cargo. The cargo transport carries everything that the crew will need, including the habitat, the Starfire reactor, the ascent vehicle, and all the supplies that the astronauts will need. This really minimizes the mass on the crew transport, and it also minimizes the transit time for them to ensure as much safety as possible on the astronauts. These are some propulsion performance metric simulation results. This is MHD code conducted at Princeton Plasma Physics Lab. And the reason why we used MHD code because the scrape-off layer, as I mentioned, it has lower temperature plasma, which has high density and more collision, so it can be approximated as fluid. So results show around 5 to 10 newtons of thrust per megawatt of power and specific impulse of approximately 8,600 to 9,200 seconds. For the lander, we use a Viking-inspired three-step descent lander. The first step is aerobraking. So we have the aeroshell that consists of bottom aeroshell and top aeroshell. The bottom aeroshell absorbs the compression heat during atmospheric entry, and the top aeroshell stores the parachute and other hardware during the entry. We then deploy a parachute to reduce its velocity further before terminal descent. And for terminal descent, we use 5 R40B engines, which are 4 kilonewtons each. So during the landing stage, we have the crew capsule, which is where the astronauts are transferred to. And we use the same capsule designed for both the landing stage and the ascent stage. So this capsule is designed for 48 hours operation. And then we also have the building of the Martian base. This is built robotically before the crew arrives, and it takes from 6 months to 1 year to complete. It's also built underground so that the astronauts are shielded from any cosmic radiation. And it also includes garden for fresh food, and this really supports the long duration stays that we hope to accomplish. For the ascent vehicle, we use a single RL-10 engine, and this uses liquid hydrogen and oxygen fuel. And as I mentioned, we can use our Starfire reactor to produce the fuel needed for this engine using the electrolysis of Martian water. So assuming 12.6 efficiency, which takes into consideration the electrolysis efficiency as well as the liquefaction process, we estimate that 28 kilograms of fuel can be produced per hour. So it would take approximately 10 days to produce the fuel needed for our engine. And another important subsystem is the electromagnetic launcher. This is also enabled because we have the Starfire reactor that could be used as a power source for it. And the purpose of this launcher is because we don't want to ignite the engine of the ascent vehicle while it's inside the lander because it would self-destruct. And this is actually something that was inspired by NASA's Mars Sample Return mission. Their Vector system, which is a pneumatic cold launch system. Essentially, what they do is they propel the ascent vehicle a few meters in the air before it ignites its engines. So we have a similar concept. However, we don't use a pneumatic launcher, we use an electromagnetic launcher. And this is much more compact in its architecture, which was more appropriate for our design. And it also has higher acceleration control. So we've done a feasibility study on a smaller scale system, and we're currently working on the full scale system. So these are some initial results that showed the feasibility of launching a 300 kilogram vehicle around 2 meters in the air before engine ignition. And then finally, for our power ascent stage, we follow the rising leg of a Hohmann ellipse, intercepting at 60 kilometers altitude, and we compute that using the linear tangent law for the optimal trajectory. And then finally, we do an insertion burn into a 300-kilometer orbit in low Mars orbit, and the crew transfers from the ascent vehicle to the Starfire transport to return back to Earth. And this is the proposed development plan for Starfire. It is a very ambitious plan, but we believe it can be done because there's a lot of shared architecture across the vehicles, and many of the subsystems can be developed in parallel to meet the timeline. And then finally, these are other mission analyses. If you're interested, the QR code will direct you to the link to other missions. And let me know if you have any other questions regarding this mission or the other mission analyses. I will be leaving my email in the description of this video. So thank you so much for watching. Make sure to subscribe. And yeah, I am happy to discuss any questions or any notes that you have to share.